So coming to the problem number 1, we have to write a code for a function which takes a type WP, WS, RP, AS and TS as input, and it gives the output of numerator and denominator in the analog domain, and we need to convert it into digital domain by using impulse invariance method. So basically my idea is to create a function which takes these inputs and calculates the coefficients of numerator and denominator in the analog and converting those coefficients from analog to digital using impulse invariance method. Let us see the MATLAB code for this thing. You can see here I have written the function my digital IAR, which takes type WP, WS, RP, AS, TS as the input, and I used strcmpi, which converts whether the string in the type is equal to the butter or not. If it is equal, this again calls a function known as butter1, and I have defined again a function butter1, file name is butter1, which takes omega p, omega s, rp and as values, and it returns the numerator and denominator in the analog domain. Similarly, for Chebi1, I have defined a function Chebi11. For Chebi2, I have defined a function Chebi21, and for elliptic, I have defined a function elliptic1. So the corresponding functions are Chebi11, which calculates and gives the outputs in the analog domain itself, and Chebi21 also gives the output in the analog domain itself, and elliptic1 same. So from this function till here, the analog uh, coefficients of the numerator and denominator are stored in the corresponding num and den. Now we have to convert this num and den into the digital using IIR. I have defined another function IIR which does this. So coming to the IIR function, so this function takes num and den and TS value and gives the output in the coefficients of numerator and coefficients of denominator in the Z domain. Now let us check for an example. I have taken passband frequency as 0.2 into pi and stop band frequency as 0.5 into pi, RP equal to 1, AS equal to 30. And now I am calling my digital IAR, and now I am calculating the coefficients of numerator and denominator. This thing returns me the coefficients in the Z domain by using the impulse invariance method, which is exactly I wanted. Now I'm storing A2 comma A22 which are corresponding to Chebi1 and A3 comma A33 for Chebi2 and A4 comma A44 which stores the values of elliptic. And then here I have defined the values for the W, so in which the frequency response will be plotted. By using the frequency command, I have taken the coefficients of numerator and denominator and then calculating its frequency response. So here you can see the order in the Butterworth is 5, Chebi1 is 4, Chebi2 is 4 and elliptic is 3. And here you can see the gain is around 0, and after stop band the gain is more than the required minimum attenuation. Even in the Chebi1 it is almost satisfying the required conditions. Till passband the gain is near to 0, and after at the stop band and after the stop band the minimum the attenuation is greater than the minimum required attenuation. As we are using the impulse invariance method, you can see here in the Chebi2 the frequencies are not mapped correctly, like we are not getting the desired response. So this is one of the drawback of the impulse invariance method. And in the elliptic it is giving almost accurate results. Till passband it is the gain is around 0, and after the stop band it is greater than or equal to the minimum required stop band attenuation. So till here I have calculated the H and plotted the response in the gain. And let's see the phase. So here you can see I have plotted all the phase of the Butterworth, Chebby 1, Chebby 2 and elliptic in the same plot. You can see all the response is totally it is non-linear, which is expected as this is a IIR filter. Now going on to the second question, we have to design a IIR low pass filter given omega p, omega s, and if you see clearly here they have given the maximum passband gain, minimum passband gain and the maximum stop band gain. And we have to design using Butterworth Chebyshev 1, Chebyshev 2 elliptic. We have to use impulse invariance and bilinear both. And we also need to plot the pole and zeros. So here how to get RP. If you see the response, so if you see the filter response, he has given in the pass band the maximum gain is 0 dB and the minimum gain is minus 0.3 dB. So RP will be minimum pass band gain minus maximum pass band gain. So which is nothing but 0 minus 0.3, which is nothing but 0.3 dB. And we are having a maximum stop band gain. So minimum stop band attenuation is equal to negative of maximum stop band gain. So this gives you negative of negative 30 dB, which is nothing but 30 dB. So now we have omega p, omega s, rp and as. Now let's see how to design this using bilinear transformation and impulse invariance method. So I have written the MATLAB code for this. I have written omega p, omega s and max pass. This is the given information, and rp is given by maximum pass band gain minus minimum pass band gain, and minimum attenuation is equal to negative of the maximum stop band gain. And I have taken ts equal to 1, which is this value. So now I'm using the previous my digital IAR to get the coefficients of a numerator and denominator in the analog domain by using Butterworth, Chebby 1, Chebby 2 and the elliptic. So here I have taken W equal to 512 points, 0 to pi, it will plot 512 samples in the frequency domain. I have plotted the frequency response of corresponding Butterworth here, Chebby 1 here, Chebby 2 here and the elliptic here. If you plot carefully, in the Butterworth, I have got the order equal to 27, Chebby 1 9, Chebby 2 9, and the elliptic as 5. So here I have used impulse invariance. So due to the aliasing effect and overlapping, you can see the frequency plot is not that much good for Butterworth. Here red is Butterworth, green is Chebby 1, blue is Chebby 2 and magenta, which is pink, is elliptic. So you can see here only the green response is satisfying the required specifications, that is at 0.6 free 0.6 top band it is having attenuation of 30 dB, whereas the other plots are having less than 30 dB. So this is the drawback of impulse invariance. It is not mapping the poles and the zeros in the from the S plane to the Z plane accurately. Even the phase, you can see here it is non-linear. And here I have also plotted the poles and the zeros. To plot the poles and the zeros directly, we can use this command z plane and a1 comma a11, which takes numerator coefficients and denominator coefficients as the input. Fine. Now if I solve the same question using the bilinear transformation, here the order in the Butterworth is 15, 7 in Chebby 1, 7 in Chebby 2 and 5 in the elliptic. And here you can see except the elliptic, all other are matching. Like see, the red one is having the exact minus 30 dB attenuation at the stop band edge, and pink color, which is elliptic. Okay, the elliptic is also having the stop band more than 30 dB, and even the green, which is Chevy one, is also having the minimum stop band attenuation required. Except Chevy 2, all the other three filters are satisfying the condition. Now, if I plot the phase, here we can see for all the three cases, Butterworth, Chebby 1, Chebby 2 and elliptic, the phase is non-linear. And if you plot the zeros and poles of the filters, this is the corresponding output. You can see all the poles are inside the unit circle, which means they are stable. Here except Chebby 2, Butterworth, Chebby 1 and elliptic are following the required specifications. If you compare the orders of bilinear transformation and impulse invariance transform, here it is 15,775 and there it was 27,995. And you can see if we use bilinear transformation, we are getting more accurate results than the impulse invariance transform. Coming to the third question, here we need to design a elliptic low pass given a sampling rate of 100 kilohertz with a passband frequency, stop band frequency, passband ripple and stop band ripple. So here RP is equal to 0.3 dB, RS equal to 45 dB, and here they have given us in the frequency in the hertz. So first we need to convert them into normalized radian per second. Formula will be omega equal to 2 pi f divided by fs. This will be in normalized form, normalized radian per second. So only this thing is changed here. So after calculating this, if we get if we take this as new values omega p and omega s, here I have written the code for the third question. So here I have taken fs, fp, rp, as, and here I have converted them into normalized form, which is nothing but radians per second. And now as I am using impulse invariance method, omega equal to w by t, here you should be careful. Here whatever value you take, it should give the same value here also, which is nothing but uh, the my digital IR function, which takes TS as the input. So once after converting into the normalized form, here you can put any value. Suppose let's see what happens if you change the value afterwards. So after calculating omega p and omega s, similar to the previous question, and plotting the frequency response, here you can see passband till passband the gain is around 0, and at the stop band you can clearly see that the required attenuation is not that much. Here we can see the attenuation is almost minus slightly more than minus 35, but our required attenuation was minus 45. So as we are using the impulse invariance method, the frequencies are not getting mapped correctly in the Z plane. So this is the same drawback of the impulse invariance method. So let us see if we change the values here. Let us say if we keep 22 here and 22 here. So this doesn't change anything. So same, we are getting minus 37, more than minus 35 at the minimum attenuation. At the stop band it is around minus 37 dB. So you need to be careful, like if you have used the normalized frequency here, no need to worry about this T, you can keep any value. For simplicity, uh, we are taking 1. Now let us see in the bilinear transformation. In the bilinear transformation, up to here everything will be same, and once we have calculated the normalized frequency, we need to first uh, pre-warp the frequencies and then calculate the coefficients by using the bilinear transformation. Here I have defined the another function, my digital IAR bili, which takes the input in the analog and returns the output in digital by using the bilinear transformation method. Here you can see the uh, my digital IAR bilinear function which I have written. The file name is my digital IAR bili. So it takes the input in the analog and it returns the output uh, into the digital using the inbuilt bilinear transformation. Here you can use a separate function. You can define a separate function and write a code for the bilinear function itself. It's just nothing but we are transforming s equal to 2 by t into 1 minus z inverse by 1 plus z inverse, so that you can write the code by yourself, or you can directly use the inbuilt MATLAB command. So after getting the coefficients in the digital domain using the bilinear transformation, now I am plotting it using the frequency command, and here you can see here the output is accurate. Here you can see at the stop band I am getting the attenuation around more than 47 dB, which is greater than minus 45 dB, so it is satisfying the required condition. And if you see before pass band, before the pass band, you can see the gain is around 0, which is still fine. And as we are using a elliptic, you can see some ripples in the stop band and even some small ripples in the pass band also, like it is not straight exactly. You can see here we are seeing some curve. And if we further plot the phase of this filter transfer function, here we can see the phase is still, it is nonlinear. As this is a IR filter, we expect the phase to be nonlinear. So coming to the fourth question, here we need to design IR high pass filter given omega p, omega s and rp, and maximum stop band attenuation is 50 dB. So we need to design all 4 types of filters using Butterworth Chebyshev 1, Chebyshev 2 elliptic by using impulse invariance and bilinear transformation. Here if you observe, they have given peak passband ripple equal to 0 dB. If you go to the formula of order for the Butterworth, it is log of 10 power 0.1 alpha s minus 1 by 0.1 alpha p minus 1 power 1 by 2 divided by log of omega s by omega p. So if you substitute alpha p equal to 0 here, we are getting log of infinite. So the order is not defined. So basically, if you want to design a filter with 0 ripples in the passband, then the order will tend to infinite. Like practically, we can't make this possible. So what we will be doing is, we will take the passband ripple in powers of some 10 power minus 9 or 10 power minus 8. We make it very small, not exactly 0, but we tend it to 0. And then let's see our observation. Using bilinear transformation, we have discussed how to design the high pass filter. By using impulse invariance method, there will be no change in the designing the high pass filter. Just the only thing you will be replacing is in LP to HP, in place of omega cap p, you use omega c, which is nothing but cutoff frequency. That's the only difference which we will be doing in the impulse invariance, and the rest is same. Here you can see I have written the code for the high pass filter using the bilinear transformation. So everything I have taken rp equal to 10 power minus 10, which is close to 0, and if we run it, here you can see the order is very high. It is 29 in the Butterworth, 15 in Chebby 1, 15 Chebby 2, and 10 in the elliptic. And as I have used the bilinear transformation, the plotting will be accurate when compared to the impulse invariance transform. Like here you can see, except the blue color, which is Chebby 2, the rest is satisfying the condition. If you see here, the red is Butterworth, green is Chebby 1, and the pink is elliptic. So you can see the minimum attenuation is 50 dB. So Butterworth is satisfying, and Chebby 1 is also satisfying as it is 51. And if you see for pink color, which is elliptic, it is also satisfying because it is attenuating more than the minimum required. It is attenuating about 59 dB. So the impulse response is fine except the Chebby 2. Coming to the code, here everything is same. Uh, Here I have defined another function, mynumden in analog. So this basically calculates the numerator and denominator in the analog domain, and it will not convert into digital by using impulse invariance or bilinear. It just gives the output in the analog domain itself, and then we will convert that analog low pass to analog high pass using our previous formula, like how we did in the example sum. And after converting into the high pass analog, now we will use bilinear transformation to convert into analog to digital, and then plotting its frequency by using frequency command, and then plotting its gain and angle. So magnitude, gain we have already discussed. Coming to the magnitude, you can see here it is non-linear except the Chebby 2. Chebby 2 is failing. And coming to the poles and 0, you can see all poles are located inside for Butterworth, Chebby 1, and for Chebby 2 they are located on the circle, and for elliptic they are inside the circle. Now if we want to design the same high pass using impulse invariance method, the only change where we will be doing is in the conversion of low pass to high pass in analog domain, instead of omega p cap, here we will be using the cutoff frequency. So this function, this output is corresponding to this function. So it gives the order and the cutoff frequency of the Butterworth, and the second one is Chebyshev 1 and Chebyshev 2, and the third one is elliptic. So I have manually entered these values from here to here, and here. So after converting from low pass to high pass in the analog, we will be using impulse invariance, the function which I have written, I have discussed earlier. So this thing, it will take the input in the analog and convert it into the digital. After converting it to the digital by using IAR, here we will be using frequency command to plot its response. Here I have plotted the output of the response. Here if you see the Butterworth, Chebby 1, Chebby 2, and then elliptic, they are not that much aligned with the required specifications, because the same thing, impulse invariance will plot from S domain to Z domain, but it because of some aliasing and overlapping of the higher frequencies itself, we are not seeing that much attenuation in the output response. Because of the overlapping, the attenuation is getting reduced in the stop band itself. So we are seeing less attenuation than the required attenuation, because the higher frequencies are overlapping and amplifying the signal at that frequency. So we are not able to see that much attenuation when compared to the bilinear transformation, because in bilinear transformation from it maps the poles uniquely in the z domain, so there will be no overlapping, so you can see the clear attenuation. But here it is different, because of overlapping and all, we are not able to see the correct attenuation at the stop band. So coming to the problem number 5, here we need to design a IR bandpass filter given omega p1, p2, omega s1 and omega s2, and here rp is given and maximum stop band attenuation is also given. So here we will be using Chebyshev 2 prototype to design this bandpass filter. Let's see in detail. So here I have written the code for the IR bandpass filter using Chebyshev 2. So here you can see first, as we are using bilinear transformation, we need to pre-warp the frequencies, and then RP is given, AS is given. First we design the specifications of low pass. We consider omega p equal to 1, and we calculate omega naught cap, and we calculate bandwidth, same omega p equal to 1, and we calculate omega s1 and omega s2, and we take the minimum value in this both, and I have discussed why we take the minimum value in detail. But in some cases, if we are getting negative values, we should ignore them. In this problem, we are not getting any negative values, but if we get any negative values, we need to ignore that value and we need to take the positive value, which is a minimum among the both. So after that, it's just calculated the order and omega cutoff frequency and numerator coefficients and denominator coefficients in the analog frequency by using a Chebyshev command, Chebyshev odd and Chebyshev command, and then converting the low pass in the analog to band pass in the analog by using the inbuilt LP2BP command, and then by using bilinear transformation we converted from analog to digital, and then plotting the frequency response. So here if you see, we need to check whether this plot is correct or wrong. So let us check. Here at stop band 1, we are getting the required attenuation was 50 dB, but we are getting the attenuation more than 50 dB, which is completely fine, which is good actually. And in between the passband edge 1 and passband edge 2, the gain is around 0. It means the how much ever input is coming to the system, the same input is coming out of the system without any amplification or loss, which is the property itself of the bandpass filter. And if you see at the stop band edge 2, even here the attenuation is more than 50 dB, slightly more than 50 dB, which is also fine, because we expect a minimum, we wanted a minimum attenuation at that point, but if we are getting more attenuation at that point itself, then it's good. The filter is working very well. So by this, like this, you can verify whether the output is, aligning with the required specifications or not. If we see the phase plot, it is non-linear, this is a IR filter, and if we plot the poles and zeros, you can see the poles are inside the unit circle and some of the zeros, all the zeros are on the unit circle. So coming to the sixth question, here we need to design a IR filter. They have not said anything, but they have not said anything about the low pass, high pass. They have given the specifications. We need to conclude whether this is a band pass or band stop. They have told to use the Butterworth and Chebyshev. Let's see. Here if you observe, if you take a rough graph like 0, 0.2 pi, 0.35 pi, 0.65 pi, and 0.75 pi, and then pi. So what they have given is in 0 to 0.2 pi, the response should be around 1.01 to 0.95. From 0.35 to 0.65, the response should be about 0 to 0.1. Here, this is pass band, and say here the response is between 0 to 0.01, and in between 0.7 pi to pi, the response is again in between 1.05 to 0.95. So basically what we are doing is we are allowing this part and this part. In between 0.35 pi to 0.65, the response is strongly attenuated. So this is nothing but band stop. We are stopping a band of frequencies in between 0.35 pi and 0.65 pi. So we know this is P1, top band 1, omega S2 and omega P2. We need to know what is AS and RP. To get AS, you can use minus log of 1 by AP, 1 by A. 1 by A is 0.01. So by using this, you will get AS. And here we need to find RP. To find RP, RP is the ripples in the pass band. Like I said in the first slide, in some cases, we will be having two different pass bands and the RP values will be different. In that case, we need to take the max RP value. So that if it satisfies the max RP value, then automatically the minimum RP value will be satisfied in this. So we calculate RP value individually for this thing, this thing, this thing, and then we will take the maximum RP value. So here I have written the MATLAB code for this RP, and then we will be taking the max RP value and then calculating the AS, and the rest is same, calculating omega cap, omega naught cap and bandwidth, and calculating two values of omega p1 and omega p2. Here we will be fixing omega is equal to 1, which is here we have done it. Here if you see, we got omega p1 is positive and omega p2 is negative. So in this case, we need to consider the lowest positive minimum value, which is nothing but omega p1, and we will be neglecting the another value. After getting this, now we have got the specifications of the low pass filter. Now we will be calculating the order and numerator coefficients and denominator coefficients, and then we will be converting it into the band stop from analog low pass to analog band pass, and then by using a bilinear transformation, and then plotting the frequency using the frequency command. Now we have got this response. Let us check whether this response is correct or wrong. So if you see till 0.3, the gain is around 0, and at the passband 2, after the passband edge 2, the gain is around 0, which is fine. And at the stop band edge 1, if you see clearly, the required attenuation was yeah, if you see, the required attenuation is 40 dB. The required attenuation is 40 dB, and at stop band edge 1, we are getting an attenuation of minus 100 dB, which is fine. And at stop band edge 2, we are getting the exactly minus 40 dB attenuation, which is fine. So like this, you can verify whether your response is correct or wrong. And if you see the phase plot is non-linear, as it is a IR filter. Now the same code, instead of using butter and but odd, I have used Chebi2 odd and Chebi2, and the rest is same, calculating low pass analog to band stop analog, and then analog to digital using bilinear transformation. And the only difference which you can see from the previous and here is you can see some ripples in the stop band. So that's what Chebyshev filter is. In the Chebyshev filter, in Chebi 2 filter, there are ripples in the stop band. And here you can see till passband edge 1, the gain is around 0. Here we can see a little attenuation here, which is fine as these are practical filters. We can't get the attenuation uh, gain 0 exactly till that point. And then stop band, at stop band the attenuation is more than the required. Even at the edge 2, the attenuation is more than required. It's around minus 48 dB. And if you see after the passband edge 2, the gain is around 0. So like this you can verify whether your expected filter design is aligning with your input specifications or not. We need to design a discrete time system h of z. Basically this is a filter, and we'll pass this xn through this filter, and then we'll get yn as output. So given input signal is this omega 1, omega 2. So we need to generate and sketch omega n. That's fine, we can do it. And we need to calculate endpoint DFT of the input signal and then plot its magnitude and log magnitude. Fine, this also we can do. And coming to the C question, here we need to remove the higher frequency component by using discrete time system HZ, and then we need to plot the magnitude of this phase response. Here given the input specifications are this. So basically here if we see the frequency response, if you take 1 here, if we take in omega, not normalized one, so mod omega less than 1, the gain should be, the magnitude is between 0 to 0.9 to 1. So here it is 1, it is 0.19, sorry. And after omega greater than 1, after 1, the magnitude should be around less than 0.05. So it should drop between somewhere around 0.05. So if you observe this clearly, here we are allowing it is passband, and here we are stopping it. So basically it is a low pass filter, and we need to design this low pass filter. So to get the from the graph, here we can see we can get the RP value. Here it is linear, so we need to get in the decibel minus 20 log of 0.9, and then AS value, AS equal to minus 20 log of 0.05. Now we have got RP value and AS value. So here stop band and pass band, they are given exactly 1. So let us see how to take this omega p and omega s in detail when we discuss in the MATLAB code. So after designing the filter, our aim is to process the input signal using this designed system and check the output. And then we'll check the output. We'll get output in the digital domain, which is digital time domain. We will convert it into frequency domain by using FFT, and we will check whether the corresponding frequencies in the low frequency region are filtered enough or not. So this is the overall idea about this question. So plotting the input, uh, transforming the input into the frequency domain, and designing a low pass filter, and then processing the input signal through this designed low pass filter, and then getting the output in the frequency domain by using FFT. So here I have written the code for this. Here you can see samples are given 100, so 0 to 99, omega 1, omega 2, and xn. It is input in the time domain, and finding the FFTs. As we are having two signs, we will see 4 peaks, 2 peaks for each sine wave at that corresponding frequency, omega 1 and omega 2. Here you can see it. So after plotting in the frequency domain, we can see 4 peaks at the corresponding frequencies of the sine waves. And here we need to design a low pass filter. Here I am using the designing the low pass filter using Butterworth and bilinear transformation. So here I have taken omega p equal to 0.99 and omega s equal to 1.11. If we take both omega p and omega s equal to 1, the order will be becoming infinity. So we will not be able to design the filter. So I have taken these values. You can take any another value which is near to 1 also, not a problem. So as I am using bilinear, I am pre-warping the frequencies and then calculating RP, RS, AS values, and calculating N and cutoff frequency in the analog domain, and then using the bilinear transformation from low pass analog to digital low pass, and then calculating its frequency response. And if I run this, here I have plotted using the normalized frequency. So here it is 0.3 into pi, 0.35 into pi, 0.4 into pi. So at omega is equal to 1.1, which is nothing but 0.35 into pi. We are seeing an attenuation of about minus 26 dB, and till passband the gain is around 0, which is fine, and at stop band I am getting the attenuation required minimum attenuation, which is fine. So now we will pass the input signal through this low pass filter. So to pass the input signal through the filter, we will be using the filter command, in which we will be giving the numerator of the filter and denominator of the filter, and then input signal. If you do this, you will get the output in the time domain. So similarly, if I further convert this output into the frequency domain, here you can see now there are only here I have used the FFT and plotted the output. So after converting into the frequency domain, so initially we had 4 peaks. Here you can see only 2 peaks are present. Like this, we will design the filters according to our specifications, and then we will pass the input signals through the filters. I know I may have said some mistakes. Feel free to correct me and comment the mistakes, and if you have any suggestions, you can comment it. And thank you. If you find this video useful, feel free to share this with your friends. Happy learning. Bye.